Okay, so as we move forward with probability, the next thing we're going to look at is how to build a probability model. Okay, and so we've built models before. Our normal curve was an example of a model. We just finished with models doing our least squares, regression lines. Okay, and so this would be how we would build a model for probability. So when we're building a model for probability, there's kind of two things that we need to keep in mind. The first one is what we call the sample space S, okay, of a chance process. And so what the sample space S is all of our possible outcomes. So if you're flipping a coin, okay, there's only two, right? It's either heads or tails. If you're rolling a die, right, there are 6 possible outcomes. 1, 2, 3, 4, 5, or 6. Okay, if you're asking somebody a question about something, every possible answer is a possible outcome. So maybe it's a question where they're choosing something. Maybe they're choosing their favorite city in the U.S. to visit. Well, in theory, all of the cities in the U.S. could be a possible outcome. So that's what the sample space is. The probability model will describe your chance process, and it's going to consist of the sample space as well as the probability for each outcome. Like, for example, if we were flipping the coin, right, the probability for heads is 1/2 or 50%, and the probability for tails is 1/2 or 50%. Okay, and so our model is going to consist of both of those, both the sample space as well as the probability for each outcome. So let's look at an example. So for this particular probability model, they're talking about playing a board game and rolling 2 fair 6-sided dice. Fair meaning they have 1, 2, 3, 4, 5, and 6 on them. Same probability for each outcome. One that's red and one that's green. And the problem here is giving a probability model for this chance process. So there are 36 possible outcomes when they roll the 2 dice. So this is our S, right? All these different outcomes here, right? We could have double ones. We could have 5 and a 1, 6 and 4, 6 and 5. The first one, you'll notice, if you look at these, you'll notice you can have, so you can have 6 and 4 right here, or you could have the first die be 4 and then a second one be 6. And those are 2 different possibilities. So there are 36 possible outcomes when we roll the 2 dice and record the number of spots showing on the up faces. Okay, so this whole thing right here is my, whoa, my line went crazy there, is my sample space S. Okay, and then all 36 outcomes should be equally likely. So the probability of each outcome is just 1 out of 36. And that since that probability is the same for all of them, they can go ahead and just state that each outcome has a probability of 1 out of 36. So that's my model. My model consists of showing all the possible outcomes. So this right here, my sample space S, and then giving the probability of those possible outcomes. And since they're all the same, it's 1 out of 36. So we can use the probability model to determine an event. So an event is a collection of outcomes from the chance process. So for instance, let's say I wanted to know all the possibilities that added up to 9, or all the possibilities of rolling doubles. That would be my event. And my events are noted with capital letters. Okay, and so when we write our notation for these things, we write capital P, which is the probability of event A equals whatever. So that's what your notation is going to look like for this. You may have event B, and that would be that would look the same, probability of event B. And of course, you would need to define what these events are. So let's say, for example, event A is sum of 5. Whoops, I don't know why I wrote E. Sum of 5. So as we look at our model here, we have 4 of them that will add up to 5. Okay, we have this one, and we have 1 plus 4, and 2 plus 3, and then 3 plus 2, and then we would also, that's 4. Yep, that's 4 of them. Okay, so we have 4 of them that are going to add up to 5. Okay, each of these probabilities, remember the probability of each event happening was 36, so we can just add those together, and so we can say the probability of event A happening, which is the sum is 5, is 1 out of 36 plus 1 out of 36 plus 1 out of 36 plus 1 out of 36, which would give us 4 out of 36. Okay, and so now you can sometimes use that to work backwards, right? Now we could say that event B is sum is not equal to 5. Well, I know that 4 out of 36 of them, the sum is equal to 5, which means the other 32 don't add up to 5, right? And so I can find the probability of event B being all of them, 36 out of 36, minus 4 out of 36, right? All of my possibilities minus the 4 that don't add up. And so the probability of them not equaling 5 would be 32 out of 36. We could also add up two seemingly completely unrelated events. For example, let's say we wanted the sum, let me get rid of this. Let's say we wanted the probability of the sum is 5 or 6. Okay, well, those don't have any outcomes in common. We don't have any combinations that are going to add up to 5 as well as add up to 6. So the combinations that we have that would add up to 6, we have 1, 2, 3, 4, 5, and then so now we have the probability of event C equals 4 out of 36 plus 5 out of 36, which is equal to 9 out of 36. So probability event of A or C. So let's back up for a second and look at that notation. Right? We had event A, we had the probability of event A, and we had the probability of event C. Okay, with C being the sum equals 6, A, the sum is 5. And so when we write this, we're looking for the probability of event A or event C happening. Okay, and I was able to add those together because none of those outcomes were the same. So let's look at some basic probability rules here. Okay, so the probability of any event is going to be a number between 0 and 1. Okay, so the probability of any event will be a number between 0 and 1 because probability is represented as a proportion, right? And the proportion will end up being between 0 and 1. Like we just saw, 9 out of 36, 4 out of 36, 5 out of 36. With 0 being the probability being that it would never happen, and 1 being the probability that it would happen all of the time. Okay, so all possible outcomes have to have a probability that add up to 1. Okay, we have to have some kind of outcome every time. So all of your possible outcomes have to add up to 1. So all of our probabilities are going to be between 0 and 1. All of our possible outcomes all possible outcomes must have probabilities that are going to add up to 1. If all of our probabilities are if all of the outcomes in the sample space are equally likely, like we saw with rolling the dice, okay, and the fact that all of those probabilities were equally likely. So if all of those probabilities are equally likely, then we can find the probability of event A, whatever that's defined as the number of outcomes that correspond to event A over the total number of outcomes in the sample space. Okay, so I've shortened that so that it fits on the iPad a little bit better. Okay, but let's go through that again. So if all of them are equally likely, if all of our outcomes in the sample space are equally likely, then the probability of the event is going to be the number of outcomes that correspond to event A, like we just saw with the dice. Right, we saw 4 of them had a sum of 5. 5 of them had a sum of 6. So the number of outcomes that correspond to whatever event it is that you're looking for over the total number of outcomes in the sample space. right? So again, example 4 out of 36. The probability that event does not occur is 1 minus that event occurring. So we saw this with the how many didn't equal to 5. So the probability of the event not occurring, so the event does not occur, is 1 minus the probability of said event occurring. And those two things have to add up to 1. The probability of the event occurring and the probability of the event not occurring, they have to add up to 1 because the event's either going to occur or it's not going to occur. Okay, that is referred to as the complement. And that is written as, so the complement of event A, and that is written as A with a C at the top, a superscript C. So what that means, that complement of A, means it's referring to not A. So for example, if we said we had that probability of event C happening, which was that the sum added up to 6, if we saw the notation that looked like this, C, I don't know what the heck happened just now to that C, with a C with a little c up to the top, that would be the probability of event C not occurring. So the outcome's not adding up to 6. And our last thing with probability here with these rules is that if two events have no outcomes in common, then the probability that one or the other occurs is the sum of their individual probabilities. This is what we saw on this on that example before when we looked at the probability of A or C, and that we were able to add those two probabilities was equal to the probability of A plus C. That's because A and C had no outcomes in common. There is no way to roll the dice and get a sum of 5, and then also get a sum of 6. Okay? When that occurs, the events are considered mutually exclusive. Okay? Events are considered mutually exclusive if they have no outcomes in common. Therefore, no matter what, the two events could not occur together. So the probability that you had a sum of 5 and a sum of 6 would equal 0. That would make them mutually exclusive. The two events could not occur at the exact same time. Okay, so down here we have a summary of what we've just been talking about. So remember, all of our probabilities here are equal to a number between 0 and 1 because they're a proportion. Okay, the sample space and a probability, all of those outcomes need to add up to 1. Basically, you need to account for all of your possible outcomes. If they are equally likely, if my outcomes are equally likely, I can just count how many times I see event A and put that over my total. Okay, remember our complement rule. So if not, okay, if I'm looking for it to be not the probability of event A, that's my complement rule, and that's 1 minus the probability of A. Pay close attention to the notation. You'll notice the notation here has the C, the superscript C, inside the parentheses. If you write the probability of event A and you apply that complement to the probability of event A and you put it on the outside of the parentheses, you will lose credit. That will be incorrect. So make sure you realize that that complement is referring specifically to event A, not the probability of event A. So your complement rule, again, is the probability of A not occurring. And then the addition rule, that's the one we just talked about with mutually exclusive. If A and B are mutually exclusive, so if they cannot happen at the same time, I can just add their probabilities together. All right, let's look at examples here. So distance learning courses are rapidly gaining popularity among college students. Randomly select an undergraduate student who is taking a distance learning course for credit and record the student's age. Here is the probability model. For part A, you're being asked to show that it's a legitimate probability model. Okay, so I need to kind of look at those rules. So is the probability of Is the probability of each outcome a number between 0 and 1? Okay, so when I look at my probabilities here, I have 0.57, 0.17, 0.14, 0.12. So that condition is met. Okay, do all of the probabilities of the possible outcomes add up to 1? So when I add all my possible outcomes, all my possible age groups, and I take all those probabilities, okay, that does add up to 1. So that would be evidence here to say this is a legitimate probability model. Okay, part B says find the probability that the chosen student is not in the traditional college age group, so not in that 18 to 23 years. Okay, so there's two ways that you could do this. Okay, so let's look at them. So the first way you could do this, so you're looking for them not to be in that traditional 18 to 23 years. So as soon as you hear that not, okay, you might want to be thinking complement rules, right? So I'm not 18. So I want to find the probability of the event that they are not 18 to 23 years old. And so to find that, I can use my complement rule, right, which is 1 minus the probability that they are 18 to 23 years, which comes out to 1 minus 0.57, which is 0.43. So basically what that says is that if 57% of the learners are 18 to 23 years old, then the other 43% are not. Okay. You also could use your addition rules here for mutually exclusive events, because if somebody is 18 to 23 years old, then they cannot be in a different age group. If somebody is 24 to 29, they can't be in the 18 to 23. So these events are all mutually exclusive. So I can add them together. So again, I define my event. So my probability that they are not 18 to 23 years. And again, because they're either in one age group or another, they can't be in two age groups at the same time, I can add all these things up. I can add up the probability of 24 to 29 years plus the probability of 30 to 39 years plus the probability that they are 40 years or over. And so when I add all those up, the 0.17 plus the 0.14 plus the 0.12, I get the same answer. I get the 0.43. So you have a 43% chance that they, when you call this person and you ask them their age, that they're not in the traditional age group. Okay, let's look at some more examples here real quick. Choose an American adult at random to find two events. A, the person has a cholesterol level of 240 milligrams per deciliter of blood or above. B, the person has a cholesterol level of 200 to 239 milligrams per deciliter, borderline high cholesterol, according to the American Heart Association. The probability of event A happening is 0.16, and the probability of point B happening is 0.29. Explain why events A and B are mutually exclusive. Well, a person can't have two different cholesterol levels. They cannot have a cholesterol level of both 240 or above, as well as, at the same time, a cholesterol level between 200 and 239. So those two events would be considered mutually exclusive. So number 2 there, say in plain language what event A or B is. What is the probability of A or B? So basically you're looking for the probability that person either has a cholesterol level of 240 or above, or they have a cholesterol level of 200 and 239. Because these two events are mutually exclusive, okay, we can add the probability of these two events together to find our total probability of them. So we had 0.16 plus 0.29, so 0.45. So there's a 45% chance that the randomly selected American adult has a cholesterol of 240 milligrams per deciliter of blood or higher, or 200 to 239 milligrams per deciliter of blood. So if C is the event that the person chosen has normal cholesterol below 200 milligrams per deciliter, what is the probability of event C? Well, the probability of event C is the probability that they are not A or B. So that would be 1 minus 0.45 or 55%, 0.55. Let's look at what we call a two-way table. Two-way tables can help us kind of lay out what's happening in our sample space and our possible options and combinations and make our probability calculations a little bit easier. So in this particular example, we've got students in a college statistics class wanted to find out how common it is for young adults to have their ears pierced. They recorded data on two variables, gender and whether the student had a pierced ear, for all 178 people in the class. The two-way table below displays the data. So we've got in this data table here, we've got gender across the top here, so male and females, and then pierced ears down the side there. We've got our totals out there on the edges, which will be helpful to us. So our problem here is, suppose we choose a student from the class at random. Find the probability that the student has pierced ears. Okay, so let's go ahead and define this event. Okay, and so we've got, well, let's look at our whole problem here. So we've got the person has pierced ears, the probability they're male and has pierced ears, and the probability they are male or have pierced ears. Okay, so let's define our events. So event A is, and you can't write an equal sign. Okay, so event A is male, and event B is pierced ears. And let's see what we can work with here. So in part A here, because we've got 178 students, they're all equally likely to be chosen. Okay, and there are 103 students with pierced ears. You can see that right here. The scenario A there, part A of the problem doesn't care about gender. It just cares about whether they have pierced ears or not. So again, since all of our students are equally likely to be chosen, the probability of event B, which is the fact that the student has pierced ears, okay, is 103 out of my total students in the class, which is 178. Part B of the problem here says we're looking for a male and for them to have pierced ears. So we're looking for them to have both of these things at the same time. So the probability of event A, that they're a male, and that they have pierced ears. So we're looking for the intersection for this. Okay? These are not mutually exclusive. I want these two things to happen at the same time. So I am looking for males and pierced ears and where those two things meet. Okay? And those two things meet they meet 19 times. Okay? So I end up with 19 out of 178. Okay? So I have my probability of males and pierced ears. So in part C then, I want male or pierced ears. Okay, so let's see. I want the probability of A or B happening. Okay, and what I need to be careful with this is that I don't count things twice. So I want males or pierced ears. So I'm looking at these males that have pierced ears, these males that don't have pierced ears, and these females, that arrow looks a little weird, these females here, the 84 females there, that have pierced ears. What I can't do is I need to make sure I don't count those 19 males that have pierced ears twice. I cannot just do my 103 plus my 90 because these events are not mutually exclusive. I would be counting those 19 kids, those 19 males that have pierced ears, I'd be counting them twice. Okay? So if I want the probability of A or B, I'm looking at 19 plus 71 plus 84 out of my 178, which becomes 174 out of 178. You'll note, and that makes sense on my table because I just have this one group of 4 women that did not have their ears pierced. And so they'd be the only ones that wouldn't fall under that category of pierced ears or males. So that last example there with the males or pierced ears, it has a rule that goes with it. Okay, so here's your rule, your general addition for 2 events. If A and B are 2 events resulting from some chance process, then getting the probability of A or B happening, which really means, when they say the probability of A or B, they really mean the probability of B, the probability of A, the probability of A and B. All of those things fall under the or. It's not a true either or situation. Like, it's not the probability of A or the probability of B. It also could be the probability of A and B. The probability that they have pierced ears, the probability that they're males, the probability that they have both of those things. Okay, and so here's how this looks to keep from our double counting. So the probability of A or B equals the probability of event A plus the probability of event B, just like you would for mutually exclusive events, but then you subtract the probability of them happening at the same time so you don't double count. This formula is actually on your formula chart, but it looks different because, of course, it looks different. Right? So the probability of A or B, so we're using our symbols here, and so we need to get used to these symbols, is the probability of event A plus the probability of event B, okay, minus the probability of A and B. Okay, so the U, that symbol there is union. Okay, and then the intersection symbol is the upside down one. So this one is the intersection. So this one is or, and this one is and. Okay, and so you'll see those symbols on your formula chart. Okay, as opposed to it written out like that there, you will see the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. All right, more examples. So a standard deck of playing cards with jokers removed consists of 52 cards and 4 suits: clubs, diamonds, hearts, and spades. Each suit has 13 cards with denominations ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. The jack, queen, and king are referred to as face cards. Imagine that we shuffle the deck thoroughly and deal 1 card. Let's define events F, getting a face card, and H, getting a heart. Make a two-way table that displays my sample space. Okay, so let's kind of think about what we're doing here, right? We have a, we have a face card, right? And I'm going to kind of abbreviate this here versus not a face card. Then we have a total there. And then we have a heart versus not a heart. And then we'd have our totals down here. Right, so our face cards that are hearts, we only have a jack, queen, and king. There are only 3 of those. Okay, so all of my hearts that are not a face card, there'd be 10 of them because there's a total of 13 hearts in the deck. Okay, the other 3 suits, clubs, spades, and diamonds, each have 3 face cards themselves. So there'd be 9 non-heart face cards, and then there would be 30 non-heart, non-face cards for a total of 39 other cards. So that gives me 52 in total there. And then I have 12 and 40 non-face cards, which gives me 52 in total. So there's my two-way table for there. I want the probability of F and H. Okay, well, I can look on my table here and I can see where they intersect. Right, they intersect right here. This is my probability of F and H, which is 3 out of 50 2, because I have 52 possible cards. Okay, and so 3 of them could be both of those things at the same time. Explain why the probability of F or H does not equal the probability of F plus H. Then use the general addition rule to find it. Okay, well, it doesn't, those two are not going to be equal to one another because they're not mutually exclusive, right? I'd be double counting my cards that are both face cards and hearts. So they're not mutually exclusive. So if I want to find the probability that they are a face card or they are a heart, then I'm looking at these 3 right here, right? The probability they are a face card or a heart would be those 3. And I can use my general addition rule to prove that by doing it. Let me see if I can find some space here. Right, so the probability of F or H would equal the probability of F plus the probability of H minus the probability of F and H. Right, so my probability of F, that they're a face card, right, would be 12 out of 52. My probability that they're a heart would be 13 out of 52, and my probability that they're both would be 3. So I'd have minus 3 out of 52, which gives me 22 out of 52 for my final probability of F or H. We can also use Venn diagrams to solve probability problems. So if we look at some of these examples here, when we talk about the Venn diagram, right? So in this first one here, in diagram A, event A is inside the circle. So there's my probability there. It's inside the circle. Okay, and the complement, so all things that are not event A, would be outside of the circle. Okay, if event A and B do not overlap, that would show you that they are mutually exclusive, right? None of them can happen at the same time. I don't have any overlap. So those two events, they have no outcomes in common, so they would be mutually exclusive. Okay, if I look down here, I can see here's my intersection there. So I have events A and B, right? So this is A and B happening together, and that would be where they overlap there. Okay, my union, which is A or B, this one I see over here, and that's all of them. That's the probability of A, the probability of B, as well as the probability of both of them occurring. Let's look at a Venn diagram example. So talking about the example we had before with the statistics class and gender and ear piercing. In our events of interest before, remember event A was that they were male and event B was that they had pierced ears. We have our two-way table here that summarizes everything. And so we're looking at being able to construct a Venn diagram that represents this. Okay, so if we look at this, we've got our one circle. Let's bring this over here. So essentially we have one circle that's going to represent males. Okay, and that would be A. Okay, and so there's our event A. We had 71 males that did not have pierced ears, and we had 19 males that did have pierced ears. So we see our 19 males fit right there in the middle where the two circles overlap, right? There's my intersection there where those two circles overlap, because event B is everybody that has pierced ears. You'll notice I've got a 4 out here outside of both circles. Those are those females, so they're not event A, and they're not pierced ears, they're not event B. So they are outside of the circles completely. So if you look here, this shows our notation here. We have events A and B, which is the green here. So A and B, right? There's my intersection there. Okay, and then we have out here, in the yellow, this is events A and not B, right? So they're not pierced ears. Okay, this is right here. This is that they are not A and they do have pierced ears. And on the outside, the 4 here, this is my not A and not pierced ears. Okay, let's look at one last example that kind of brings everything together here. So in an apartment complex, 40% of residents read USA Today. Only 25% read the New York Times. 5% of residents read both papers. Suppose we select a resident of the apartment complex at random and record which of the two papers the person reads. So here's what we're trying to do in this problem. We're making a two-way table that displays the sample space of this chance process. Construct a Venn diagram that shows us the outcomes. Find the probability that the person reads at least one of the two papers. Find the probability that they don't read either paper. So let's look at, I think this will be a lot less messy. So let's look at this. Let's look at what's written out here with our solutions here. So we're going to define events A as reading USA Today and event B as reading the New York Times. So our events are defined for us right there. From the problem statement, we know that the probability of A is 0.4, B is 0.25, okay, and we know the intersection is 0.05, where they read both papers. That's my intersection. They do A and B. So I can enter the value of 0.4 as the total in the yes column for making my two-way table. So here's my two-way table that I'm making down here. So I'm looking at reading USA Today. Okay, I can write that 0.4 of them is my total of the ones that read USA Today, which means 0.6 of them do not, because they either read it or they do not. Okay, I know that 0.25 read the New York Times, which tells me that 0.75 does not read the New York Times. Okay, I also know that 0.05 reads both of the papers, so that leaves 0.35 to only be reading USA Today. Okay, and I can do that for my total, right? 0.4 minus 0.05. And then, so if 0.05 read both USA Today and the New York Times, and I know that 0.25 read the New York Times, okay, I can subtract the 0.05 to get my 0.2 that only read the New York Times. They don't read USA Today. And again, using my total, if there are a total of 0.6, okay, then I know that 0.4 of them are not reading the New York Times as well. Okay, and so that would go ahead and complete my two-way table there of my sample space. So then my next part was to create a Venn diagram that shows my outcomes. Where's my Venn diagram? Where's my Venn diagram? So my Venn diagram that shows my outcomes here. A is still defined as reading USA Today. Okay, and so I have there's my intersection, the green in the middle. Those are my people that read both New York Times and USA Today. That's my 0.05%. Okay, out here is my 0.35 that only read USA Today. Okay, out here is my 0.2 that only read the New York Times. And out here's my 0.4 that don't read any paper at all. So for part C, we're asked to find the probability that the person reads at least one of the two newspapers. Okay, so what we're looking for here is our probability of A or B, right? We're looking for the union. We're looking for the probability of A or B. Get rid of some stuff here. Okay, so if I'm looking for the probability of A or B here, right, I can use my general addition rule, and I can take the probability of A, which is 0.4, right, the probability that they're going to read USA Today, plus the probability that they read the New York Times, minus the probability that they read both of them, so I don't count those people twice. Okay, and I get a 0.6. a probability here of 0.6. If I need to, when I need to define and explain and interpret that, okay, I'm going to tell them that there is a 60% chance that the randomly selected resident reads at least one of the two papers. Okay, you could also not just write this. We've already defined. We define these up here, what A and B is. You need to make sure that whenever you're doing a probability problem that you define your A and B or C or D or whatever it is that you're looking for. But you have to define those probabilities. Part D wants the probability that they don't read either paper. Well, I know the probability is 0.6 that they read one or the other. So the probability that they do not read either would be, I would use my complement rule there, and it would be 1 minus that. Okay, so you can see the notation for it here is a little bit crazy. Okay, so here's your notation here. The probability of the complement of A, so meaning they do not read the New York Times, okay, and then the probability of the complement of B, again, meaning they do not read, I'm sorry, that one's not reading the New York Times. The probability of complement of A is that they do not read USA Today, and that would be 0.4. Probability of them reading neither paper, which could also be, again, that's, you'll realize, you see that's the same as the 1 minus 0.6. That's what's out here in my Venn diagram. And if I bring my two-way table back, let's get that all the way over there. If I bring my two-way table back, I can see that my people that were no for both papers there, that is 0.4. So we'll do a whole bunch of probability practice problems both in class, and hopefully you'll be doing your ones on your own in preparation for building upon this.